What if every single choice you make, even just the flicker of a quantum particle, what if that creates an entirely new reality?
That's a heck of a thought, isn't it?
Yeah.
Makes you stop and really think.
Yeah. Welcome to the Deep Dive. Today we're getting into one of modern physics' most, well, mind-bending theories, the many worlds interpretation, MWI for short.
Right. And it sounds like pure science fiction sometimes, but it's actually got deep roots in quantum mechanics. Hugh Everett III first proposed it back in 1957.
A truly radical view of reality.
Absolutely. Offers a completely different picture of, well, everything.
So our mission today, our deep dive, is to really unpack this astonishing idea, the core of it being that all possible outcomes of a quantum event, they actually happen.
Mm-hmm. But in separate parallel universes.
It just fundamentally changes how we might understand existence itself. So to really get this, maybe we should quickly touch on the wave function first. That seems key.
Definitely key, yeah. So at the heart of quantum mechanics, you've got the wave function. It's basically a mathematical description, right? It holds all the potential states a system could be in.
Okay.
Now, the standard picture, the Copenhagen interpretation, says when you measure something, like look at a particle, that wave function collapses. It just snaps down to one single outcome, the one you see.
Right. Common sense view, almost.
But Everett looked at that and said, hang on, is that collapse really necessary? Is it an extra piece we don't maybe need?
So MWI is like a workaround for the collapse. What does it say happens instead? Say you have that particle, it could spin up or spin down.
Well, MWI says the universe just branches, it splits.
Different splits, yeah.
So when that quantum event happens, you don't get just one outcome, you get both, or all of them, if there were options. One whole new universe where the particle spins up, another completely separate one where it spins down.
Wow.
And both aren't equally real. They just evolve independently from then on. And crucially, the observer, the person doing the measuring, they get entangled too.
Entangled?
Meaning their state becomes linked to the particle state.
Wow.
So the observer also splits. There's a version of the observer in the spin-up universe seeing spin-up, and another version in the spin-down universe seeing spin-down.
That is staggering. Okay. So beyond just getting rid of the collapse problem, which sounds elegant, I guess, are there other quantum puzzles that MWI handles maybe better than other interpretations?
Well, one of its big selling points is consistency. It treats everything, quantum systems, measuring devices, observers, the whole lot under the same rules. Just the basic Schrödinger equation, which describes how the wave function evolves smoothly over time.
No special dividing line between tiny quantum stuff and us big classical folks.
Exactly. No arbitrary cutoff. It's all quantum, all governed by the same fundamental law. It provides this consistent deterministic picture. No weird interventions needed.
Okay, but a theory this big must have some pushback. The obvious one seems to be you can't test it, right? You can't visit these other universes.
That's the major critique, absolutely. Since these universes branch off, and as far as we know, don't interact again, direct proof is incredibly difficult, maybe impossible. It leads to a lot of debate. Is it really science if you can't test it directly?
Right. And philosophically, wow, what does it do to our idea of me if there are countless versions of me?
Exactly. Huge philosophical questions open up. Personal identity becomes really fuzzy. What about free will? If every choice just leads to a split, did I really choose?
And how do we even explain probability? Why does it feel like flipping a quantum coin gives us 50-50 odds in our world if both outcomes happen anyway?
Yeah, explaining the Born rule, the probability rule within MWI is another complex area people are still working on. There are ideas like involving self-locating uncertainty, but it's not fully settled.
Yet, despite all that, it seems like MWI is actually pretty popular among many physicists. People like Sean Carroll really champion it.
They do. For its proponents, its mathematical elegance and logical consistency in explaining quantum mechanics without extra ad hoc rules like collapse. Well, that's very appealing. They see it as taking the math of quantum mechanics seriously to its logical conclusion.
So if we try to pull all these threads together, what does MWI really tell us about, reality itself?
I think what's truly profound is how it completely reframes our place in the cosmos.
Yeah.
It suggests we're not in just one universe.
Right.
We're living in a vast, maybe infinite multiverse, an ever-branching tree of realities where every quantum possibility, every fork in the road becomes real somewhere.
It definitely goes beyond just physics. You see it inspiring philosophers, people studying consciousness, and like we said, tons of science fiction. It forces you to ask really big questions about your own existence. So the thought to leave you with is this. If there are countless versions of you out there, living different lives in these parallel realities, spawned by every quantum flutter, maybe every choice.
What does that actually mean for your identity, for your sense of free will, and for the universe you're experiencing right here, right now?
Some pretty deep questions to keep exploring.